will be an important topic in our project because since we'll be analyzing, lots of data about particular stars, so you'll need to know where that star exactly is. And last week, Akanksha had used a certain coordinate system to get the position of a star. And so I believe knowing how we get that coordinates will be pretty important for our project. So yeah, please go ahead. Thank you.
So I have just made I went through the literature and I just presenting a very abstract definition. Okay. So guys, let us consider the Earth, and this is how the Earth actually revolves around it in its axis, as we all know. And we call this the North Pole, and because we are considering we are studying the celestial coordinate system, so we call this North Celestial Pole, and we call this the South Celestial Pole. And similarly, this is the line of the equator, so we call this the celestial equator line. So this is how we actually define it. So the equator is when we study in the celestial coordinate system, we treat this upper half part from if we take from here, then this is 0 degree, and if we say a positive 34 degree, then we would something mean like this. And if we say 45 degrees, then it should be straight something like this line. And so, and similarly, then if we go to the the opposite side of the Earth, that is this surface area below, then we call this the because this is the positive, then it's similar understanding that we would be calling this the negative. So this is if this is the 34 degree, then if we see a very similar mirror image here, which would be somewhere here, so this would be minus 34 degrees. Similarly, you call this north south celestial pole the negative of the every angle that we will be observing. And one other term that is not being positioned here, but if we consider anyone standing, suppose you're standing just outside your home or in a field where you are observing the stars, then the point that is directly above your head, for example, a person for example is standing here, then the point directly above his head, for example, this is a person is standing here, and this is the point directly above his head, so we call this the zenith angle. Okay. So I suppose all of you are familiar with the vernal equinox. So it is just the position of the sun that we observe. So there is this two aspect, that is right ascension and declination. Okay. So let us when the sun is in the vernal equinox, then for example, sun is here in the vernal equinox, then this is the line that we would draw. Then the line that is eastward direction to the sun, we call that the right ascension. Okay. And so this is what we call the right ascension. It's a very important term. So a line, an angle which is eastward from the position of the sun at the time of vernal equinox, that is what we call the I'm sorry for that, the right ascension. And similarly, for example, if we based on the equatorial coordinate system, we observe the location of a star to be at using the equator that is here. Okay. And using this, we observe the star, and from this axis we find the star to be, for example, here 45 degrees, and or for example 34 degrees. So that is what we call the angle of declination. So for example, we want to observe that how to plot using these angle of declination and the right ascension. So for example, you are standing here on the equator. I'll try to zoom this. Is it being zoomed in?
Yes.
Okay. So suppose that this is where you are standing right now. I suppose like India is not visible from here, but we would just take this point here. I guess this is South America. Okay. So for example, you are standing here, and the point that is directly above your head right now, this is the zenith. So from the equator, you find your position to be at somewhere, I think, in South America, it is 34 degrees. So you are at a distance of 34 degrees from the equator. So this angle would be something like this. I suppose there may be a drawing tool here. If we and I guess if we can, okay, it's not, it doesn't. Okay, seems like I don't know how to make a line from here, but I guess you can understand, like when I'm saying that this is at an angle of 34 degrees when we are with respect to the equator. Are you guys able to follow till now?
Yes.
Anyone else? Like, are they facing any doubts? Okay, so let us say that the angle of right ascension, that we, for example, this the position of Sirius when we observe it, it is found to be around 16 degrees from the equatorial axis. And okay. The actual the angle of ascension of the uh, right ascension angle. I don't know what I'm making the mistake here. So angle of like right ascension angle of Sirius is the 16 degrees 42 arc seconds. So let us see here, like you are at an angle of this 34 degrees from the equator, and you want to observe the Sirius. Okay, like where is Sirius located from your position? So it's a very normal mathematics. So you are standing right now here, and Sirius is somewhere along this 38 degree 16 degree line from the equator. So one would ask that if I want to look at the Sirius, then like what should like where should I look so that I can locate the Sirius? So what you would have to do is that it's a very normal mathematics. So what we would do is that, for example, this is your position, but I'm just writing 34 minus 16. That would be equal to 18. So if you are standing here at 34 degree and the position of the Sirius is alongside here around 18 degrees, so you would have to look like towards the position of equator, okay, at 18 degrees towards the equator.
is there some issue?
Subjit,
Yeah, I'm here. Actually,
uh,
issue with my
we were,
network.
yeah, actually from the past 5 minutes there was lag.
For the past 5 minutes.
Yeah, actually like it was breaking in between.
I'm so sorry. I'd been just speaking. I didn't know that.
And I think even
Where
the screen is not shared. Yeah.
where did I leave?
Last time I heard was 18 degrees. We were calculating the position of Sirius.
Can we speak up?
Um, you were talking about calculating the position of Sirius using normal mathematics. Last time I heard was 18 degrees.
Okay. Okay. So I got your point. Okay, it's a bit different. Okay. It is 16 degrees minus 34. Sorry for that. Okay, so if you are standing here along the line of 34 degrees, okay, and the position of Sirius is somewhere around 18 degrees here, so you would have to uh like go towards, like face towards the equatorial line and look at an angle of 18 degrees into the sky. So for example, you are 34 at a 34 degrees here, and Ceres is here along 16-degree line, so you would have to look at the position of 18 degrees along the night sky. Then you can like pinpoint the exact position of the Sirius star. And if I suppose that, for example, now you are at a 34-degree angle here again, and now you have to observe a star that is at a position of, let us say, 55 degrees. So now you would, the person that is facing here, now you would actually have to turn around. And if it is 55 degrees, so now 45 minus 18 is 45 minus 34 is 11. Oh, sorry, 55 minus 34 is 21. So this you would have to turn around and see towards the north pole at the direction along of like 21 degrees. So you see, if you are here, so you see actually somewhere along here 21 degrees. So that would enable you to pinpoint the exact position of that particular star that you wish to observe. I'm still audible, right? I don't know if is this any network issue again.
You're audible.
Okay. So yeah, this is this. But if you, let us say, if you want to observe a star that is at minus 28 degrees, somewhere alongside here. So what you would do is that 34 minus of this 28. So that would give you sorry, minus 28 minus 34. So that would give you minus 52 degree. So you would have to turn and look at this minus means here. So you would have to look at here along again at at a angle of minus 52 degrees. So this is how you actually observe it, and this is a more practical demonstration. Okay, like this is north celestial pole. This is the angle of declination, and this is the right ascension. There exists like a more horizontal, a new coordinate system that has been proposed. It is this horizontal. We call this the horizontal like celestial coordinate system. So here we use the horizon and like this equator and the horizon as a reference, and you use these to actually pinpoint the stars, and this is actually used very widely these days in like in the telescope equipments, like any equipments that we see these days. It has been embedded with this. So for example, you have been given a telescope, uh like we are given the stellarium, and we are asked to pinpoint like the exact time, date. So what happens is the stellarium asks our coordinates as per this celestial coordinate system. And those celestial coordinate system are actually like through the correct mathematical terms, they are transformed into this horizontal coordinate system. This is also known as alt Oz. So I'll just refer to it as from now on as alt Oz. So you convert it into the alt Oz coordinate system, and like you can actually pinpoint the position of the star from the like your corresponding position that you are holding at the particular time. So for example, like one of the main advantages of this model is that was I audible before? Was there a time lag before?
Yes, I think in between got cut.
Okay. I'll just repeat. Okay, one of the main advantages of this particular system is that like the efficiency of this is quite great, and like we get to save a lot of data consumption also. But the physical coordinates that we get from this system, for example, you are in India, so that is, I guess, from the equator, it has a distance from example 63 degrees, and from that 63 degrees and the exact time and exact position, when they are transformed into the alt-Oz coordinate system, then those coordinates accurately describe your position, but they do not have any other essential meaning rather than the one that is being used here, like for the coordinate aspect. So this is how we actually like use celestial coordinates to pinpoint the exact positions of the stars, and using that data we can locate at what point do we need to look at or pinpoint our telescope to exact the like to have the exact position of the star. And last I checked, these like techniques are also used in Hubble Space Telescope to pinpoint the exact position of the star that it wishes to like take pictures of. So that's it from my side. Any questions?
I have a doubt.
Okay. Shanmugh?
Yes, I'm here.
Yeah.
Yeah. So when we are like considering in this last slide, when we are considering angle from the north pole, right? So it the coordinates of a star should remain same at all the time, right? With respect to the reference or the observer. But as we know, the Earth is continuously revolving around the sun. So this north and south are considered only with respect to Earth, right? But
Yes.
the Earth is moving, so the coordinates, if we are taking, suppose we are saying 30 degrees from north, so at different point of time, the 30 degrees of north will point to a different thing.
Yes.
So how can we like the coordinates of the star will change continuously because the Earth is moving. So how to cancel that effect? How do we take that effect into consideration?
There are a lot of data observatories like that are there that can give us the exact position of the star at any point of time. So through that we can actually detect the position at any point instant of time.
But isn't there any fixed reference so that the like you're saying the star's coordinate will you're agreeing that the star's coordinate will change with time?
Yeah.
Uh, can I add a point to this thing? So
Sure.
hi Atul. So you're asking the coordinates of the star will be changing, right? So I don't think that is the case. That is not how we see the coordinates of the star.
So if if a right ascension and a declination are given to a particular star, like say for Sirius, if something some RA and dec are given to this Sirius, right? So they don't change actually. So what happens is that the way that we see will be different.
Sorry to interrupt. Can you speak a little like louder? You're not that much audible.
Okay. So am I louder now? Louder now?
Yeah.
Is it okay? Yeah. So what happens is that the RA index doesn't change actually. So what changes is the position of the Earth changes. So suppose, for example, the RA, the declination angle, the right ascension value for Sirius is, say, for example, 6 hours. Okay. So what happens is that, so if in a particular, what is actually meaning, what is the meaning of 6 hours actually? It means that it is ahead of, it is 6 hours ahead of the sun's position. For example, if the sun is on March 21st, exactly on March 21st. Why is the reference point taken as March 21st? Because the March 21st is the equinox date, from which we will be calculating our RA and dec positions related to that. Okay. So on March 21st, if the RA is 6 hours, it means that it is 6 hours ahead of the sun's position. For example, if the sun is setting exactly in the horizon or rising, so we need to, for example, it is actually setting, right? So ahead means 6 hours. 6 hours is a one-fourth of this 24-hour cycle, right? So we should be seeing directly to the zenith. We can find the so exactly we can directly find the Sirius, right? So here, what happens is that when Earth is trying to revolve around the sun, so for every 1 month, it revolves for 30 degrees. 30 degrees accounts for 2 hours, right? So 2 hours, for every 2 hours, it actually decreases every month. So on March 21st, if it is exactly at exactly on the zenith when the sun is in the set position. So in April 21st, it is not going to be in the same position as in the zenith that is being seen on the March 21st. It will be at 4-hour place because the Earth has already revolved for 2 hours, right? So that is how it changes. And not the exact position of right ascension directly changes. So we already have a reference point on March 21st, that is 6 hours. So with respect to the season or with respect to the month that we are in, we can calculate. But suppose we are in the June 21st, March to June is 3 months. So we can say there will be 2 hour difference, right, for every month. So 2 into 3 is 6 hours. So the right ascension for Sirius will be 0 hours on June 21st. That is how it is calculated. So it is very easy to calculate when you are trying to calculate or understand the coordinates of a star. I hope I'm clear about it, or did I just confuse everything?
No. You cleared the confusion.
No, actually, in my presentation, I'm actually going to do a small exercise on actually finding exactly the points. So in that, you'll get an even more clear picture.
Okay.
So any other doubts? Any doubts from any others, or any points that they want to add, or anything? So if there isn't, then I think I can go with my part. I think.
Yeah, with one thing I want to ask is, did you did you guys study about Epoch?
Yeah, I'll cover that in my presentation.
That's fine.
I wonder. I don't think I have enough knowledge on Epoch, but I'll just give the main important indications that should be given.
Yeah, all right.
So, any doubts, or can I continue with my presentation?
You can continue.
Yeah, thank you. Is my screen visible?
Yes.
It's visible.
Sorry. One second.
It's not visible now.
Yeah. One second. I've just pressed F4 instead of F5, so it just got closed instead of getting into full screen. Yes. So, is the screen visible now?
Yes.
So, after what Sujit had said about right, ascension, and declination, they are all like the universal or the core coordinate systems that so far we've been using, right? But using them, we still have a biggest problem that we haven't noticed or we haven't seen. The problem is that the problem itself is the reference point, which we call as an equinox, right? We have calculated our right ascension from the point where the equinox has started. So the sun is exactly at the point of the equator of which the sun exactly is at the equator of the celestial sphere, right? That is the reason why we have accounted this equinox as our reference point. So what happened with the equinox? What the problem is that due to the precession of our Earth, for like almost like for every 20 to 25,000 years, the equinox changes. Like it directly shifts from one place to other place. It is like a complete difference. Like from east side, it turns to west side. That is a difference, but still we have 25,000 years, right? That is a bigger year. But still, even in duration of this 25 years, there will always be a small changes because of the precession of the Earth. So in order to have a more accuracy, what people have done is they have come with a more generalized coordinate system, like complete celestial coordinate system that we have been using since many days. So so there should be some body or there should be some organization that should be always keeping an eye on the position of an equinox, because that is what is the core of the reference point that we have been considering for the celestial coordinates. So if the core itself is changing in a celestial coordinate system, that doesn't seem right. So what they have done is they have to always look up and keep updating the core of the change in the reference point details. So what they have come up is that so the first one that they have come up is that in some years they have seen that there is a difference in this position of an equinox. Okay, so after this position after this change in position, almost the coordinates of the stars have been they have there is a big difference in the change of this coordinates of the stars. So what they have come up with an idea is that have a more variable and generalized coordinate system for this thing. So they have given name called Epoch. This Epoch decides where exactly that equinox points at that particular time. Okay, so this is Epoch. Epoch is a place where at the point. Okay, so Epoch is a place where exactly the core or the reference point of the coordinate system lies, and they will be updating regularly where this reference point is. So this reference point in terms of astronomy is called Epoch. So what all these observatories do is that they use some different coordinate systems in order to represent their epoch. So there used to be something called SK4, which you can see here. So this SK4 has an epoch of B 1950.0. So what is this B is a Brazilian equinox in that time before 2000, or it is the first epoch that was discovered and given a name B 1950, and the term that and the coordinate that is associated with that epoch is SK4. And after then they have seen another difference in 2000, and they have named it as Julian epoch. That is the reason the name J2000. So for every 50 years they'll be continuously watching this change in the reference points, and they'll be giving the updated things so that the accuracy of finding a star or celestial object doesn't change. So that is the whole concept of understanding the coordinate systems. Okay, so this ICRS is International Celestial Reference System. Okay, and this GAL is Galactic Celestial Coordinates, GALS. So these both coordinate systems use the same Julian 2000 epoch, so that they get an exact accurate coordinates of a star in terms of RA and X. Okay. After this, we'll do some exercise, so we can keep this as a bit interactive. So what exercise is that? Before going into the mathematical part or calculations part, what actually is to summarize everything. So angle of declination is it tells us where to look in the sky, and right ascension tells us when to look in the sky. At what time do you have to look in the sky in order to see that particular celestial object? And the angle of declination is the point where in the sky we have to look in order to find the star or a celestial object. So, for example, so already Sujit has said has represented the angle of declination and right ascension. Only to give us a brief summary. So if I say we are in India, right? So India's latitude is somewhere along 17 degrees. So if you are standing on 17 degrees, and the Sirius okay, I'll go into the calculation part. It will be more easy. So we have a couple of stars and celestial bodies where we can depend on. We can see, we can verify, we can prove the positions of R and decline, find something. So first one is I'll go with the Capella. Capella is a star in the constellation of Auriga. So we'll start first with the declination, and then we'll go to the right ascension. So it is the most easiest. It is more easier to find out in that way. So if you know where to look, then you can decide on when to look. Okay. So these two are the important parameters of finding a star or seeing a star in the sky. So what happens in declination? The Capella's declination is about 45 degrees. So if I am standing, if I'm in India and my latitude is 17 degrees, because latitude and angle of declination are kind of similar things, because latitude is above Earth and angle of declination is on the celestial sphere. That is the only difference, and everything else is same. So we can directly rely on that, comparing latitudes and angle of declination. So for angle of declination, the declination of Capella is 45 degrees, right? So if I'm in India and my latitude is 17 degrees north, if I'm standing on 17 degrees north, now I have to know where I have to look. Okay, so there's a 45 degrees angle. So if you are seeing a 45 degrees angle, you won't be seeing Capella because you are already at 17 degrees. So you have to subtract the 17 degrees where you have come. So you can get an exact place where you can see the Capella, star Capella. So 45 minus 17 is anyone? 45 minus 17, any math intelligence? Right.
Minus 25.
So sorry, I didn't get you.
It's minus 25, 45 minus 70.
Yeah, so if you can see in that angle, you will find the Capella star. Okay, at that angle, the calculated angle, 45 minus 17. You can see the star at that place. So now you got where to look in the sky, right? Now you have to know when to look in the sky, because 17 degrees is always there, but the edge should be also coinciding the place, right? So at what time you can exactly see. So on March 21st is the exact coinciding spot of this ecliptic, ecliptic and the equator. So at that point, at the equinox point, on March 24th at 5 hours the head of sun, you can see at the angle of 17 minus it's 32, right? So at some angle, some 27 degrees, you can exactly see the Capella and you can spot it. So now it is April, right? So we are close to April 21st. Now if you are coming to April 21st, as I've already said, because for every 30 days the Earth rotates about 30 degrees angle. Every day is 1 degree. So 30 days is 30 degrees. So 30 degrees accounts for 2 hours. Okay, so 15 hours, approximately 15 hours accounts for 1 hour. So for 30 degrees, 30 degrees accounts for 2 hours. So if you have to look up for Capella in April, you have to subtract by 1 hour, because we are in between March 21st and April 21st. You can directly decrease by 1 hour. So if you can see by 4 hours, so if the sun is at the in the set position, going to the zenith, 4 hours from zenith, 4 hours zenith in the direction of 22 degrees, you can find Capella exactly. The same goes for Sirius. So if what it means, Sirius minus 16 degrees, is that it is below this equator. So in order to see that, you have to get a certain time. Now you can't see Sirius because it is below your horizon level, right? Because it is minus 16 degrees. So you are at 17 degrees. 17 minus 16 is always 1 degree, and 1 degree is exactly to the horizon. So at March 21st, it is exactly in 1 degree, which you can't see. So in order to see that above horizon or passing through the meridian, you have to see at a spot where it is visible in the night time. So from March 21st, if you can calculate 6 months is 12 hours. So this 6 hours becomes plus 6 plus 12, sorry, plus 12 becomes 18 hours. 18 hours in the evening, right? Evening is the time where we can see the stars. So at evening, at 1 degree, you can see the Sirius. But still 1 degree is at the horizon, right? So if you can wait for another 2 hours or 3 hours, it just comes. It starts to arise from the north, and you can just see. You can see the Sirius around December, starting from November and December. So that is the correct time when you can see the Sirius, and that is how you spot where to look and when to look for a particular object, if you know right ascension and declination. So if anyone wants to say, when can we see M51? M51 is a galaxy, which is a whirlpool galaxy. So can anyone tell about M51? When can we see, and at which place, and when can we see it in the zenith? Any calculations? When?
Yeah, so we can see M51 at 30 degrees, and
Okay.
and because 13 hours means I think in the as far as I understood, it's in the like in the noon, so we cannot see. So
Yeah.
So we have
So
to take 6 hours more, like in the 3 months. After 3 months.
no, 6 hours. Yeah. Okay. 3 months.
Yeah.
So 3 months from now is like almost July. So in July at 6 o'clock, you can see at 17 degrees exactly. Sorry, at 30 degrees, you can exactly see M51, but not with our naked eye, obviously, because it's a galaxy. So that is how we actually calculate this thing. And coming up to the magnitude systems that we have to see in order to see, or in order to find a star in the sky, we have to first see the star. How, if we know the property or the brightness of a star, it is even more easier to understand. Like if I say you can find M51 in at this time, at this spot, you cannot directly go and see for ages. If M51 shows up at some time, you cannot directly see, right? That is because of the brightness of the galaxy. You can also, the distance between it is many light years from Earth, right? That is the reason we can't see. Also because it being a galaxy, though it have a very good amount of stars, it don't directly show up in the night sky that we see. So understanding the brightness of the star is even more important after understanding the coordinates of the system. So what actually is the magnitude of a star? Magnitude of a star is nothing but it's just a measure of a brightness of a star. If something is more brighter, the magnitude is very less. It's like a rank. The more brightness, it get a first rank, and the first rank is its magnitude. And if it is very fainter, it gets like sixth rank or seventh rank. So it is very faint for a naked eye. Speaking of naked eyes, the naked eye can only observe until 6th magnitude system. But if you are staying in a city, the capitals of states, I think you will be confined to see only like up to 3. 3 is also a great number. You can only see the zenith part of up to 3 magnitude stars. not more than that. I can bet on that. If you go some outskirts or very good place or area, you can see up to 5 to 6 magnitude stars, not more than that. You need to have some equipment, maybe a telescope or binoculars, in order to see the next order of magnitude stars. So how do we calculate this magnitude stars? Like before calculating, what are the types of magnitude that we actually use in order to define a star's magnitude? So we have two different types of magnitudes. One is called apparent magnitude, one is called absolute magnitude. Apparent by name itself is something called approximate, not something that is universally applicable, something that we want to see. So by the name apparent, not the apparent magnitude. So what apparent magnitude is that the brightness of a star from Earth, like how we see the night sky. We see the night sky. So this is the Sirius, Sirius in its constellation. In this constellation, so Sirius is the brightest star, and we see many of the stars that are less brighter than Sirius. So this is a representation of this constellation as observed from Earth. Okay, so in these apparent magnitude, we see that the Sirius is more brighter, and the stars that are around in that constellation are very much fainter. That is called apparent magnitude, that is relative to the Earth. So if you want to find the exact, how much exactly is the Sirius, how much exactly is the stars that are around in the same constellation, that is something called absolute magnitude. So what happens in an absolute magnitude? How do you calculate it? So you bring every star to a certain distance, you keep them one beside the other, you see how much brightness they are exactly, how bright they are, how luminous they are exactly. Like if I am at a place of 10 kilometers, and if I have a big flag or a red flag, you can see me at some spot, and if I have 20 kilometers, if I have a flag, you can see me at a different scale, right? That is how apparent magnitude happens. But what happens in absolute magnitude is that every spot in this, every celestial object in this universe are going to 10 parsec. 10 parsec is a reference point for everything. So we bring up everything to this 10 parsec level, and we observe the stars. Okay, so we observe the stars, then we exactly know. That is something called absolute by its name. So that is how you exactly know the brightness of a star. So if in that case, if you can see, Sirius is the most fainter one in this thing, and every one that is around in this constellation are more brighter. You see that is absolute magnitude. That is how we see. But what actually we have been learning since our childhood is that Sirius is the brightest star. But that is the apparent magnitude that we're talking about. That is not absolute magnitude. If we are talking about absolute magnitude, that is exactly how the star is. It is exactly how we have to see for taking some measurements, or for taking for understanding the properties of star. That is something that we look for. That is absolute magnitude. So how do we look up? Is there a problem in changing of the slide? Oh, that is nothing.
No, you're still in the same Capella slide.
Oh.
Yeah, in the third slide.
Oh, sorry. Okay, I'll just then reshare. The Capella slide. Can you see my screen share now?
Yeah. Now you're in the magnitude system measure of brightness of star.
So, okay, I'll just do a quick recap in order to coincide this visual presentation in my words. So what actually is the magnitude, how bright an object is. It is a measure of brightness of a star or some celestial object, any celestial object. Okay, so that is magnitude system, and there are two types of magnitude systems. There are apparent magnitude and absolute magnitude. So apparent magnitude gives us the magnitude of a star that we see from Earth, and absolute magnitude is something that is observed at some place, some specific place, that is 10 parsecs, that is being globally used and accepted by everyone. So that is absolute magnitude. If you want to find some properties of a star, if you want to understand the properties of a star using spectroscopy or some kind of equipment, understand understand everything about a celestial object, what you use is the absolute magnitude, not the apparent magnitude. Use apparent magnitude mostly for the naked eye, understanding of naked eyes and all. That is where apparent magnitudes are used. So how do we find this magnitude of a star? So coming to the apparent magnitude of a star, so any brightness of a star or any measure of luminosity is always in the scale of a logarithm. Is in the logarithmic scale. So that is how we find out brightness of a star or magnitude of a star. So what actually happens is that we cannot directly find the magnitude of a star by seeing it. We have to have a reference point. So that is how we find brightness or magnitude of a star. For example, if you have to find the mass of a star, we refer to the solar mass, right? Solar mass, we have given a reference point as 1 to sun. So anything above it is more than solar mass. That is the term, right? Solar mass. It's the mass of the sun, and this much times the sun mass. This much times it is heavier than sun. That is solar mass. If something is 5 solar masses, it is 5 times the mass of the sun. The same way, if we have to understand the apparent magnitude of any star, we have to have a comparison between 2 different stars. Then only we can find the magnitude of a star. So here m2 minus m1 is equals to minus 2.5 log of b2 minus b2 by b1. This is something. I will say the brightness of a star is always measured in time in the logarithmic scale, and m2 and m1 gives us the difference between the magnitude of 2 stars. As I said, magnitude can only understand by having a reference star and the star that we want to see. So m2 is star that we are observing, and m1 is a reference star. So suppose we have a reference star, say suppose m1.
Shanmukh,
Yeah.
are you still on the 4th slide?
Types of magnitude, yes.
Okay.
Yeah, I'm on the 4th slide. Yeah. So coming to the absolute magnitude. So what happens in absolute magnitude is that absolute magnitude gives the relation between the apparent magnitude and absolute magnitude, by which we can find the absolute magnitude directly. So we have to find the apparent magnitude in order to understand the absolute magnitude, or find the value of an absolute magnitude. So as I said, the brightness is always in the scale of a logarithm. So from the inverse, from the this distance scales, we can directly find the absolute difference ratios, brightness ratios between 2 different stars, and we can find the absolute magnitude that way. So these 2 are the formulas, and I suggest you go through these formulas even more in order to understand how we exactly find the magnitude of stars, how we find the magnitude of different celestial objects. So how do we actually see in a star chart of having among exactly in the constellations, how do we put them in a star chart? That is what we will see here now. So here the Sirius is a brightest object. So here we are talking about something apparent magnitude here. That is the reason why Sirius is more brighter. So most of the times when you have to point out know the position of a star, when we have to name the position of a star in the sky, we use apparent magnitude. For if you want to do inner deep understanding the properties of the star, something we use called absolute magnitude. It depends on what kind of work you do. So here in this star, we see the kinds of stars in this constellation, that is constellations around the Sirius that is in this Canis Major constellation, and the other constellations that are surround this thing. So we can see how big this Sirius is and how big this Agara star is. This is how the magnitude of stars are represented. So if we can see in the down, if you can see beside this AIU Sky telescope below, you can see the magnitudes of the star are represented. So if you want to find this beta, this thing, you can directly match it to this thing. So you can say this beta star is actually the Sirius beta. So this Sirius beta star has a magnitude of 2. So magnitude of star 2 can be seen with the naked eye. So it is easy to see these kind of stars with naked eye if you have a good night sky view or something like that. So what is below zero? Below zero is also represents something even brighter than magnitude stars. So -2 doesn't mean that it is even fainter, it is even brighter. So we have given 0 as a reference point to Vega. Vega is having a zero magnitude. Zero magnitude doesn't mean zero brightness. It has a highest brightness, and we give a reference point to that because it is a star. And anything that is below zero are mostly the planets and the sun that we see, because they have a relatively very less distance than the stars and other celestial objects like galaxies or something like that. So this is a star chart that we can see and point out how bright the stars are in a constellation or in the chart. So this is what happens usually when we want to point stars in our with naked eye. So if we are living in a city sky, that is how you see. These are the stars that you usually see. And if you have this excellent dark sky side, only these are the only ones you can still see. This is a single field of view of a night view, and they are divided into different kinds. Like at this point, you'll see these kind of stars and like that. And finally, I want to end up pointing out at something different that we have been pointed out in our project, something called B minus B ratio. So what actually is B minus B ratio is it is a color ratio. So why do we need to have a color ratio? Because we have already know what is the magnitude of a star. Not only magnitude of a star is a property of a star that we want to know, we can also know the color of a star in order to understand the temperature of the body. So we are getting this black body spectrum in our project, right? So in order to understand the black body spectrum of any star or any celestial object, the base that we want to see is the color. So if something is very blue, if I can just go to the first thing, you see very blue stars in this nebula, right? So actually, blue stars have very huge temperature in them. So very high temperatures gives the blue color, and the very low temperatures gives the red one. That is the reason why we see the like red color is the mostly seen in our daily life. If we can heat some metal thing, we can only see the red color. That is what we are limited to. That is the only heat that we are limited to on our Earth. But we have to. What happens when a large energy is fusing, and what happens if we have huge temperatures? So the color changes to different things in this their pattern. So if you have something yellow, that is a middle, that is a midpoint of this temperature, the highest and the lowest temperature. The highest temperature is the blue color. So having this B minus V ratio is a color ratio. We can find the temperatures of the star surface, and this ratio is almost equal to this absolute magnitude formula, and by this we can find out the B minus V ratio. So that is how we can initially start our project, I guess. So this is something I've found out while reading. Thank you. Oh, sorry. Okay. I'll again share. I can see my third slide. Now you can see, right?
Yeah, but when you explained your PPT was stuck at post slide.
Okay, no problem. This is a small one. I can just again show you. So as I've already said, that the magnitude of a star doesn't give the whole set of properties that we know to understand about a star. We also need something more about a star. So what we see is about the next after the brightness is the temperature. So so in order to understand the temperature of the surface of a star, what we use is that we understand the color signs of that star. Color signs means if something is very if the star is red, we say it has a relatively low temperature compared to the temperature of the blue one. Blue one is the highest temperature, which we see in the younger stars. and yellow ones are like our sun, which are yellow. Capella is yellow. In the same way, Betelgeuse or those kinds of stars are kind of red, which means that they are in the later stages of their star stellar evolution. So by this colors, we can color ratios of different stars. We can understand the surface temperature of different stars. So I think BV ratio is something that we need to understand in order to understand the black body spectrum, the curve that we have got using this archival data from this year. So this BV color can be obtained from using the brightness of the absolute magnitude formula, which is minus 2.5 log 10 log B brightness of the star by BV to the base 10. So there is a relation between this absolute magnitude and the BV color. So I think this can be our initial understanding to the project that we have to start to progress it in a good way. So that is it from my side. Thank you. Any doubts or any points that anyone want to add? Or any discussions if someone want to have?
Yes, one thing I want to point out is that B minus V color is just not for B minus V, it's for like, UV also and RI also. It also goes with it actually with the filters, right? So how much intensity is coming in this region? Let's say in the blue region, how much intensity of light is coming? And then you subtract it to get, and then in the violet region, so the classic, the mostly used ones are the U for ultraviolet, B for blue, V is for green yellow, and R and I for red and infrared. So you basically measure the intensity of light from the star in that region, and then you subtract it to get to come to get that difference, and then you make your analysis on that.
Okay.
And so that's what we'll be doing here in this project also.
Okay.
Here, MB and MB represents what?
I believe it represents apparent magnitude, right?
Yeah, right. The apparent magnitude of this blue and apparent magnitude of this visual.
And BB and BV are the absolute magnitudes, right?
No, they are the brightness ratios of this blue and visual.
Absolute magnitude is always in capital M.
Yeah. Small m represents this apparent magnitude. Yeah.
So yeah, Shanmukh and Sujit, thank you for today's session. Please put the resources and this PPT is also in the channel.
Yeah, sure.
Discord channel. And I think you guys were you were talking about some exercises, right, for the coordinate system. So make some 3 to 4 questions on there and then put it up there. I think it'll help others progress.
Can you repeat the first part? I just missed you both.
So you made some questions, right, for the coordinate system, some kind of puzzle kind of yeah. So you put them up in the channel so that it'll help engage others also. They can solve it, and then you can check the answers there.
Yeah, sure.
Yeah, cool. Yeah, all right, then thank you for today's session, and then I think we can stop now there. Do share the resources.